COVID-19 vaccine for COVID-19 vaccine efficacy. The presentation online, we start with the motivation behind the study, and we'll look at the objectives of the study. Then we proceed to the model formulation, and then the properties, including the basic reproduction number. Then we delve into epidemiology-informed neural networks, deep learning architectures, and the hybrid neural networks. We will proceed to deterministic results and investigate the vaccination impact. Then after exhausting the deterministic aspect, we'll move on to the stochastic vaccine model, then to incorporate noise into the model to examine the behavior and the noisy data. We'll proceed to the behavior epidemiology-informed neural network. So we begin with background and motivation. COVID-19 was declared a global pandemic in 2021, yes, and we all bear witness to that. And vaccination remains the most effective long-term control. Most institutions impose social distancing and other factors to control the viral spread, and they were not really effective because of non-compliance of humans. So as it stands, vaccination is the most effective long-term control strategy. So with the objectives, this research focused on developing COVID-19 efficacy model, vaccine efficacy model, SIR model, and incorporating epidemiology-informed neural networks and stochastic informed neural networks after extending the model to a stochastic differential equations, and then and also went further to incorporate behavior dynamics, how behavior of humans can influence the dynamics of COVID-19 transmission. So we look at the model, the vaccination efficacy model with 3 compartments. The idea or the inspiration came from Kenmark model in 1927. So we basically extended that model by incorporating vaccination and then vaccination efficacy rate. So beta in this model represents transmission rate, and then we have gamma representing recovery rate, we have nu representing vaccination rate, and we have eta representing the vaccine efficacy. So we explored in the model, this aspect of the model, the properties of the model was explored to see whether it's really a feasible model. It's a model that can be reliable to some extent, because the classifications were based on 3 compartments: as susceptible, infectives, and recovered populations. So in that case, we decide to prove the non-negativity, in other words, positivity of the model, by resolving all these state variables, and it was proved that at any time greater than or equal to 0, these state variables will assume positive values, and that was proved. So the model was later explored for the boundedness, that there's a particular value that all the populations sum up together. That's the 3 compartments: susceptible population, infected populations, and the recovered, will always be bounded above by this factor, 1 divided by nu eta, where we've already defined what nu is and what eta is. So we further went on to explore the basic reproduction number, the secondary infections. I mean, a factor that determines how many people an infected individual can infect or transmit the virus to in the entire life spent infections. So we realized that this value beta divided by gamma as the basic reproduction number. And this value is so important in deciding whether the virus is going to die out or is going to persist or hold the population. So when this value is found to be less than 1, it means the disease is going to die out with time. And it simply means in layman language, each infected or infectious person transmit the virus to less than one person. In a situation where we have the basic reproduction number, that's the R naught greater than 1, it basically means that an infectious person spreads the virus to more than one person, or at least one person. Um, and then when it is equal to 1, it basically means that the virus is not spreading and it's not also wiping out. So it's actually at the threshold and remains stable or persistent. So epidemiology informed neural network. This is inspired by physics informed neural networks by Racing 2019. Epidemiological constraints embedded directly into the loss function solve the epidemiology informed neural network solves the inverse problems of learning. That's the parameters beta and gamma, including the infected compartment or population. Epidemiology informed neural networks gives an automatic differentiation, which is used to compute time derivatives. And then, so we take a look at a basic, a flow chart or something, what we call a schematic diagram of an epidemiology-informed neural networks. So this is defined by the tangent hyperbolic function uh, after receiving data from the input layer, and to the hidden layers, which compose of the tangent hyperbolic function, and then later transmuted. This data is encoded in the loss function. The loss function uh, is created with respect to the model parameters with the infected data, the data we're going to use for the prediction, and the initial values regarding. When we look at it, we'll consider all these things. And then the epidemiology informed neural networks will be giving out, or to be producing our parameters beta, gamma, and then the infected populations. So basically, this is the schematic diagram of the epidemiology informed neural network. So the loss function, which is defined as, in fact, we define the loss function as L equal to MSC sub data plus MEC. So basically, it's the mean squared error of the data. I mean, the deviation in the data and the predicted data we're going to get, and that of the model parameters, and then with the initial conditions as well, if there are deviations in the model parameters, all these deviations will combine to form our loss function. We talk about the residuals. The residuals will be encoded into the loss function, and these are defined based on our equations. The susceptible, the infected, and the recovered population, defined by the equations as seen here. That is basically the derivative of the susceptible population with respect to time, subtract, taken as, let me say, basically the main equation. Let's look at the main equation so that I can explain this carefully. The main equation is here. So basically, we take it this way, that all these functions are taken out of the derivative of the susceptible population with respect to time. So whatever is going to be left is the residuals. So basically, it's also a form of deviation. I mean, what is left. So we move on further to, so we have residual 1, residual 2, and residual 3. That's with respect to susceptible population, infected population, and the recovered population. So we're looking at recurrent neural networks. We're going to use 3 variants from this neural networks. Recurrent neural networks, in fact, they work in a form, they work in a way that whatever is produced as an output is taken again as an input and then reapplied for the cycle to continue. That's how they work. So we're going to look at long short-term memory, that's LSTM. And then we look at the bidirectional long short-term memory. We look at gated recurrent unit. There's a schematic diagram of the long short-term memory. Data is this is the input sector. Data is input in this. Then all this is transmitted to the layers within the architecture and then given out through the output layer here. So we move on further to the schematic diagram of the bidirectional long short-term memory and the gated recurrent unit. So, and this structure, this is the basic schematic structure or architecture for these uh, diagrams. So we have them here. This neural networks, recurrent neural networks. Then we move on further to residual neural networks. This is the hybrid form of neural networks that works with several dynamics. Residual networks behaves like a numerical ODE solvers. They learn system dynamics through residual connections, denoted by this equation we have here. Then we move on to the residual network architecture. It basically looks like this. This is how it looks like in and then out. Detailed architecture is given in the diagram on the right here, where we have it here about, we have hidden layers, two hidden layers here, taking in data and then pass through the hidden layers with the help of the necessary functions, the loss functions, and then these are finally given out in the last section. Then, so as I said earlier on, the hybrid models, which are the residual networks, we will also be based on the long short-term but directional short-term memory and the gated recurrent unit. So their workflow is such that epidemiology-informed neural network learns epidemiological parameters. The residual networks capture smooth dynamics. Recurrent neural networks perform short-term predictions. That's basically how the workflow symbolized. And then we have a deep learning forecasting workflow like this. The COVID data is intaked here. We have what we call data pre-processing. This pass through the training. The data is actually splitted to 2080. And then for training, 80 for training and 20 for testing, or what we call validation. And then this is passed on to the various recurrent neural networks. We have the long short-term memory, bidirectional long short-term memory, the gated recovery unit. Error matrices are produced in each of the recurrent neural networks, and these are compared. And then we use the evaluation, what we call cross-validation. We'll be able to determine which of the recurrent neural networks produces better results or performs better in this case. So we come to data description and pre-processing. COVID-19 data from Tennessee Health Health Department. The data is from Tennessee Health Department, taken from the period of 2020 March, September 2021. So then basically we're going to look at the data fitting parameter and the confidence intervals here. So data pre-processing and data fitting. We look at one, this place, let me see if I can zoom this. I don't think it's zoomable. Okay, so we look at this place with Tennessee. We have the real data and then that of the predicted data here. So when we look at this carefully, we have the vertical axis and the horizontal axis. Horizontal for days, and the vertical is for the coming. And if it meets me, it's like I can't see it well myself. I'm coming. So we have yes. So yeah, let's go to the right hand side here. So we have the fitted data. So we look at a bit deviation here, which is it's almost matching the actual data, but there's a deviation somewhere here. Then we also have kind of meeting coming. Okay, so basically data pre-processing, data fitting. So the A is the data at the top there. So we have data fitting, the graph, and then the B is basically talking about how the predicted data compares with the actual data, what we have there. Then we have gamma here. You remember gamma is the recovery rates, confidence intervals of 95, and then we have a transmission rate of 0.34 with a confidence interval of 95%. We look at the beta prediction of the beta at different frequency levels here. Proceed on to, we realize that increasing vaccination rates reduces peak infection size, and then it also reduces time to peak and also reduces basal reproduction number. And then we also realize that higher vaccine efficacy accelerates disease elimination. And this is illustrated here too. So we have A and B here. The population, the vertical axis stands for the population. That's what we have these values here. So we have the behavior, the vaccination rate of 1% and 3%, and vaccination rate of 6% and 10%. So 1% is the top left, and then the 3% is the top right. And we come to the bottom, that's the B, where we have 6% and then 10%, basically. And then we look at the behavior of the susceptible population and the infected population, the recovered population at different vaccination rates. That's basically what this diagram is talking about. So we look at the behaviors here. So we see the um, red line stands for susceptible, and then the infected is the continuous line, and the broken line stands for the recovered. So we can see how the dynamics behave at different vaccination rates in these diagrams. Then we proceed on to vaccination impact with 80% efficacy. With 80% efficacy, where this is the behavior, beta 0.35, gamma throughout to the days of peak, which is 46. And what does this really mean? Let's look at this. Graph 2, we have the 94% efficacy rate of vaccination, and then the beta. So we can compare this basically, and we can make some deductions here. With efficacy rate, vaccine rate of 0.5% here, the transmission rate was 0.44. And then with this 80, we have transmission rate of 0.45. Basically, even standing on this, we can say that when the efficacy was higher, transmission rate was reducing. We can study that clearly here. We also realize that with the gamma, which is actually the recovery rate, the gamma, which is actually the recovery rate here, we can see gamma to be the behavior of gamma here. When the efficacy rate was high, what happens? Gamma behaves in this situation, 22, 0.5 gave us 0.22. Then we have 0.5, the same 0.22. The behavior doesn't really vary much. This is because efficacy rate actually doesn't directly affect the infected population. It affects the susceptible population by moving a lot of individuals from the susceptible class to the recovered class. That is why the behavior of gamma is not really very conspicuous here. And then basal reproduction number 2, we look at the behavior of the basal reproduction number with respect to the vaccine efficacy. So we look at the basal reproduction number here. The values are corresponding to the vaccine rate here, moves this way. So when we look at this, we can make some deductions too here. So obviously, basal reproduction number is higher in most of the rates here at 80% efficacy than 94% efficacy. What does that mean? When the efficacy of the vaccination is high, it basically means that less people will transmit the virus, and then a lot of people will move from susceptible class to infected, recovered class, resulting in less people who will move from the susceptible class to the infected class. So we move on to prediction performance. We're going to look at the prediction performance with result to the error matrix, the root mean square error, and the mean absolute percent error, explained variance. So with the habit models, we realize the habit models outperform standalone recurrent neural networks. So we look at the habit model prediction here. With the habit model prediction, data-driven simulation for residual network, short-term memory, residual network, bidirectional long short-term memory, and residual network data recovery unit. This is the behavior and of this model, the hybrid model, predictions, daily cases, residual network, and then each of the lines we can see the colors highlighted with the name recurrent neural network, residual recurrent neural networks here. So we move on to this graph to look at how the error metrics are compared. With a long short-term memory, we actually compare two error metrics. That's the root mean square error and the mean absolute percent error. So we look at how these errors are compared with respect to the different neural networks that were applied. So that's the long short-term memory. We see how it moves with the root mean squared error. And then comparatively, we look at the right-hand side, that is the mean absolute percent error. And that is the basic comparison of the two error metrics. Then we continue to say that, okay, best performing models, we can say residual network for the gated recurrent unit. We have the lowest root mean square error and the lowest mean absolute percent error, and then the highest explained variance, as illustrated throughout these comparisons. Then we went further to still look at the following error metrics. We look at root mean squared error, mean absolute percent error, and the explained variance. And then we compared all this with the various neural networks that we applied. And then the values comparatively are shown on the table 5 here. Long short-term memory 650 approximately, and then bidirectional 611. So when we look at the root mean square error for each of these neural networks, we can see that the one that produced the least root mean squared error is the residual network gated recurrent unit. That's what produced the least here. And then we also look at the mean absolute percent error here. The list basically is the same as the root mean squared error. Explained variance too. When we look at explained variance, we have the list to be the bidirectional long short-term memory. So based on this, we made the following conclusions. Epidemiology-informed neural network successfully learns epidemiological parameters. Hybrid residual network gated recurrent unit yields superior prediction accuracy. Yes, as could be seen here with the lowest root mean squared error. So it made the best prediction, or more superior prediction. Vaccination rate and efficacy significantly reduce disease spread. Framework integrates epidemiology, deep learning, and uncertainty quantification. So this is the conclusion we made from the deterministic aspect of this model. Then we proceeded to the stochastic, where we are going to consider a lot of factors, environmental factors, inconsistency with data, inconsistency with other factors that directly affects model or disease dynamics. So we use the Brownian motion and then the noise intensity, and then this product of this was incorporated as our noise term to look at the behavior of the disease dynamics in the presence of such inconsistency that we call noise. Then we looked at nonlinear incidence rates, capture behavior effects, saturation, psychological inhibition, and then we consider the parameters kappa, k, h, and then alpha. Both are considered to be greater than 0 in this function, what we call the nonlinear incidence rate. Then we went further to apply physics-informed neural networks, develop a loss function with respect to the data and the residuals from the model, and then we define this as our loss function. So physics-informed neural networks with a practical schematic diagram, we have it here, and then we talk about the input, and then the hidden layers. We'll talk about the loss function being incorporated here and coded inside the physics-informed neural networks here. Then We look at extension of the pins. We enforces SRR model structure, and then this model actually learns the state variables, and then through and also goes further to predict the parameters beta and gamma. Then we look at epidemiology informed neural network structure, basic schematic structure. Also look like this with ODs. So this is the system we are going to extend. Instead of ODs, now going to be what? Stochastic differential equations, because we incorporated stochastic entities to the model, or inconsistency data in other factors, inconsistency in other factors or data into the model here. So with the extension to stochastic systems, we use the Euler-Maruyama discretization, Monte Carlo averaging over stochastic differential equation realizations. Then this is the new structure after the extension to stochastic differential equations. So we look at the structure here with the input, data fitting and parameters inference, trainable parameters beta and gamma with the fixed parameters. Yeah, we are not going to actually predict all the parameters. Some of the parameters will actually be fixed, and we will train and then predict other parameters. So the parameters we're going to train the beta and the gamma, that is the transmission rate and the recovery rate. So the loss function is defined here also, mean squared error, the model with respect to, and the deviation from each of the state variables after prediction, we call the data loss. The actual COVID-19 data and noisy data for the state of Tennessee from 2020, 17th December to May 16, 2020. We're going to look at two graphs. The left graph shows the susceptible group, while the middle and right graphs shows the infected and recovered groups, respectively. So we're going to look at different noise levels, 5%, 10%, 30%, and 60%. And then this is what is illustrated here. We have the data here, with the actual data being the broken lines we're seeing here, 5% noise, shown by red, and then blue is the 10% noise, green is the 30% noise, and yellow is the 60% noise. So we look at the behavior of the susceptible population, infected population, and the recovered population at different noise levels. So when we look at this, we study this carefully, we can see the behavior dynamics in these three figures. Okay, so we compare at 5% noise, stochastic epidemiology informed neural network, it fits noisy data better. It fits noisy data better. Let's go back and check that with the 5%. We can see that this data really looks a bit clustered. Yeah, it's not really that scattered much as compared to the other ones where the noise is high. So we move on to, so this is where we are supposed to talk. Yeah, the noisy data. This is more clustered. That's the susceptible here. And then we have the infected here with 5%. We look at the 5% here for the recovered. If we consider these values, we know that epidemiology informed neural network against stochastic epidemiology informed neural networks at 5% noise. This is what this diagram is basically talking about. So at 5% noise, we look at the behavior of the deterministic and the stochastic. Deterministic graph, you can see that one here, and we have the stochastic graph somewhere here. So we look at the behavior, a bit deviated here, 5% noise, but the higher the noise, the more the distortion. You can see the two of them are being distorted. Here, not even close at all. One is predicting better, one is more affected by the noise. Then we move on to the recovered also here, the behavior of the stochastic and the behavior of the deterministic in the recovered class at 5% noise. So with the comparisons at 50% noise, both models degrade, and then stochastic epidemiology informed neural network still captures trend better. And that is what conclusion we can make from this. When we move on further to the 60% noise level, we are seeing another dynamics here or behavior here with the deterministic and the stochastic at 60% noise. We look at the behavior of these two models, and then we look at the behavior of the infected in both stochastic case and deterministic case. And then we do same for the recovered. And then based on this, we can see that, oh, my this is my screen. This part is not coming. I don't know. Okay, 5% noise and 1% vaccination rate. Excellent fit of the nonlinear transmission. Stochastic epidemiology informed neural networks captures nonlinear dynamics. And then so we move on to the nonlinear incidence rate again against this as stochastic epidemiology informed neural networks. When we look at this at a 5% noise level, we look at the behavior of this nonlinear incidence rate at 5% and 1% vaccination rate. This is how it behaves against the nonlinear incidence rate and against the infected class. So both at 5% noise and then at 1% vaccination rate. This is the behavior. This is quite close. So at 60% noise and 10% vaccination, data fits very poor. There is a poorer fitting of data, as can be seen here. Yes. Then the noise and vaccination interact strongly, and that is what resulted in the poor fitting of the data. So we move on to data-driven simulation for nonlinear incidence rate, 60% noise with 10% vaccination rate. So then we look at the behavior at this place very carefully. We have the data here, the stochastic epidemiology informed neural networks at the nonlinear incidence rate. And then we have the behavior to against the infected class. Then we can see a more scattered behavior of the nonlinear incidence rate here against the stochastic epidemiology informed neural networks of the infected class. Then the root mean squared error and the mean absolute percent error values became significantly higher, suggesting a larger discrepancy between the predicted values and the actual data. This indicates that the model struggles to accurately predict the nonlinear incidence rate under conditions of higher noise levels. That's why we are seeing the scattered behavior here. Higher vaccination rate of 10% general results in slightly higher root mean squared error and mean absolute percent error. And higher vaccination rates may introduce additional complexities into the model. So this is what we are seeing. Basically, this table explains better the previous slides. So it's such that when we look at this error matrix for nonlinear incidence rate, the 5%, 10%, 30, 60% at a different noise level, we look at the vaccination rates too of 1%, 10% throughout. Yeah. Then we look at the eta, that is the efficacy rate of 94. We realize that the root mean squared error and the mean absolute percent error at a 5% noise error and at 1% vaccination rate resulted in these values, 654 and 0.0087. So this comparatively, when we look at the root mean squared error vertically, with relative to the different noise levels and the different vaccination rates, we realize that let's pick the lowest and then make a deduction. We have the lowest to be 10, no, it's not 10,000, it's 5,470. That occurs at 10% vaccination rate and then 5% noise level. Then when we look at the mean absolute percent error, that basically also occurred at the same stage. So what conclusion do we make? It means lower noise level at higher vaccination rates will result in a lower error of prediction. Okay, so we look at sensitivity analysis. Sensitivity analysis examines how changes in model parameters influence model outputs. So we go into it is used to evaluate robustness of the stochastic epidemiology informed neural network framework, stability and architectural changes, validity of model predictions. So and this sensitivity analysis was performed by varying number of hidden layers, number of neurons per layer, the regularization parameter was fixed at there. So we're going to look at how sensitive the prediction will be. I mean, how accurate or inaccurate it will be with respect to the variation of these two things. That's the hidden layers and then the neurons per layer. Then we also have the regularization parameter, which was fixed at epsilon 10 exponent negative 1. We look at the error parameters, error metrics here, root mean squared error, mean absolute percent error, and explain variance and relative error. So performance was evaluated on these errors. So in table 3, which is in the next one, table 3, that's this table. Models with 32 neurons. So let's go back there and study that we come back. We have layers 3 to 5, and we have neurons from 32 to 64. So we're looking at something here. When neurons are kept, layers are kept at 3, and the neurons are increased from 32 to 64, what happened to root mean squared error? The root mean squared error was basically increased as well as neurons increase. The mean absolute percent error also went up. The explained variance went up, and then the relative error also went up. So what does it mean? Keeping layers constant and increasing neurons will increase the error. So we move on, and then keeping layers, we increase the layers at this stage to 4, and then we look at the neurons. So four layers, 32 neurons, we had 3,493, and 4 layers again, 64 neurons, we had 4,159. There's also a behavior over there at this stage compared. So when we move down further to where we have a lot of layers, the highest number of layers, that is 5, against the neurons, we realized that as layers were increasing, the errors were able to come down. The root mean squared error came down. So it tells us something that to get better predictions, we need to increase our layers, and then also look at how to regulate the neurons against the layers. So classical epidemic models neglect human behavioral dynamics. So we are going to look at behavioral epidemiology informed neural network, or behavior epidemiology informed neural networks. That really incorporates human behavior. COVID-19 virus is basically more of human influence because the virus is spread more when humans interact. So based on that, this work, the authors incorporated behavior dynamics to study how they influence the spread of the virus. So we have the compliance with mitigation measures strongly affect disease transmission. So the compliance factor is what they are going to, where they considered here. They consider the compliance factor here as a behavior that can directly influence the dynamics of COVID-19 spreading. So the next, we look at COVID-19 transmission is influenced by the following factors: social distancing, mask usage, mobility reduction, public adherence to policies, and then behavioral responses evolve over time. People behavior evolves over time. Of course, this is obvious. When we cast our minds back in 2021, 2020, when people were being forced to stay indoors, I mean, a lot of people were rebelliously and going out, and I mean, it could confirm the fact that behavior responses evolve over time. It takes time before people get used to a certain form of behavior. So ignoring behavior leads to bias transmission estimates. Yes. So this is the model with the compliance factor C of T incorporated into the dynamics. So we'll look at the compliance factor in here. Susceptible against susceptibles, the rate of change of susceptibles per time, and that of rate of change of infected per time. Then we make the assumption that the compliance rate lies between 0 and 1, inclusive. So if the compliance rate is 1, it means people are complying strictly to the rules or the norms. Stay indoors. Everyone is staying indoors. No one is going out. I mean, that means 100% compliance. If people are not complying, at all, then that means it should be 0. Otherwise, the compliance rate will depend on how people behave, which will lie between 0 and 1. So compliance rate of 0, that's what was explained earlier. No adherence to mitigation, and then compliance rate of 1 is full adherence. Behavior epidemiology informed neural networks does not assume a predefined functional form. Yes, compliance is learned directly from epidemic data. B asterisk of t, that is beta of t1 minus c of t, and then we have the effective reproduction factor here. Increasing compliance reduces transmission rate. What does that really mean? So if the compliance factor here is increasing directly, then it means the transmission rate, that is beta of t here, will obviously go down because the function here algebraically 1 minus c of t, once c is increasing, the result in the bracket here will go down, and that will ultimately affect the transmission rate, which depends on these factors. And then compliance dynamically alters epidemic potential. Good. So when we also look at this carefully here, the effective reproduction number here, which is a factor of the transmission rate, the recovery rate, and then the natural death, and then the compliance factor, will also still be affected by the compliance rate here. When the compliance factor here reduces, then it means that effective reproduction number will obviously go up, but or remain at a particular state. But if it increases, it's going to reduce the denominator here, and that will reduce the effective reproduction number. Then we look at the behavior-informed neural networks. It's actually inspired by physics-informed neural networks, and it shows it's an extension of the PINs, or physics-informed neural networks. It is this kind of model is actually deployed by embedding behavioral dynamics. Yes, the dynamics of people behavior into the disease dynamics to look at how they behave, how their behavior can affect the disease transmission. So we learn this simultaneously, these state variables, and then these parameters, behavioral compliance factor C of T. So behavioral epidemiology informed neural network, that's the BEINN, with a schematic diagram illustrated here. Input data travel all the way. A lot of the loss function applies here. And then this with respect to the regularized parameter and its loss as well. And then giving out predicted values of the parameters and the state variables. So separate neural networks for each compartment, and separate neural networks for each time varying parameter, and the input, which is the time t, and the output variables and parameters were state variables and parameters were what was produced after the behavior epidemiology informed neural network was deployed. So with the loss function here, we have data fitting loss, and then that's L sub of data, and then we have the OD residual loss. Then we have the regularization parameter. That also affects to some extent how the model will predict accurately. Then we look at epidemiological residual constraints defined by this system with the transmission rate and the compliance factor also playing a role in each of these steps. Then we move on straight to say that, okay, input COVID-19 data regularization parameter epsilon, interpolate data using cubic splines, and then compute data and residual losses, minimize total loss using Adam optimizer, and then learn compliance and epidemiological. This is what the behavior epidemiology informed neural network does, the algorithm does. Yeah, this is basically telling us what it does. Then data in steady region. So we look at the data that was used for this research. The data was used from three states in the United States, Tennessee, New York, and Michigan. And the period as was indicated earlier, that's March 30th, 2020 to December 16, 2020, normalized by population size. So behavior epidemiology informed neural network capture distinct compliance patterns across states, Higher compliance observed during early outbreak phases, pins and beans yield different behavior estimates. And this is what is illustrated here for the three states. Compliance rate against the data here. So look at the behavior of the two neural networks. There's the pins and the behavior epidemiology informed neural networks in the three different states. Also, we impact of compliance on transmission rate, the inverse relationship observed, higher compliance, lower transmission, consistent across all states. So basically, this is understandable. Yeah, higher compliance means lower transmission, but the opposite will result in higher transmission. Then we look at the effects of compliance rates on transmission rate for Tennessee, New York, and Michigan using behavior epidemiology informed neural networks here. And this data also stands again for the Tennessee state, New York state, and Michigan state for the compliance factor or compliance state against it. And then this illustrates the behavior of the model in these three states. So the metrics used in this study or that will help us to evaluate the performance of these models basically will be the root mean squared error, the mean absolute percent error, the explained variance, and the relative error. Based on this analysis, the behavior epidemiology informed neural networks outperforms the pin across all states, as illustrated in this table here. So we have the models illustrated here, and then CPU time, root mean squared error, mean absolute percent error, explained variance, and relative error. So we look at them carefully, and then after studying this table carefully, we came up with this conclusion that behavior epidemiology informed neural networks outperforms the physics informed neural networks as illustrated across this table. So with a general conclusion, we say that stochastic epidemiology informed neural networks outperforms deterministic epidemiology informed neural networks under noise. And the stochastic modeling is essential for epidemic data. Nonlinear incidence rates capture realistic transmission. Framework useful for policy and vaccination strategies. So we will look at deterministic against stochastic modeling. What was really deduced? What can we actually deduce when we compare these situations, a deterministic state and then the stochastic modeling? Comparatively, analysis showed that the stochastic models outperform the deterministic model in capturing real epidemic dynamics. Stochastic epidemiology informed neural networks effectively incorporated randomization or randomness and noise through stochastic differential equations. The error metrics such as root mean squared error, explained variance, and relative error consistently indicated lower prediction errors for stochastic models, better agreement with observed data. That was illustrated in our findings in the previous slides. These results highlight the importance of accounting for uncertainty in epidemic modeling. So we went further to look at the sensitivity and the regularization analysis. Sensitivity analysis demonstrate that model performance depends strongly on these three factors: the number of layers, the number of neurons, regularization parameter. At a certain regularization parameter, the model was found to be performing better, producing lower errors as compared to a certain regularization parameter. Then we also look at optimal performance was achieved with 5 hidden layers, 32 neurons per layer, and with a regularization parameter of epsilon, which is 10 exponent minus 1. Appropriate regularization, we have prevented overfitting. That's the work of good regularization. If you regularize, use the correct regularization parameter, then it's going to prevent overfitting. It's going to improve numerical stability and then also enhance generalization. So with the behavior or behavioral epidemiology informed neural networks, which incorporated human behavior into the disease dynamics, the results show that compliance rates vary over time. It takes time for people to comply with whatever social interventions that you put out there. Behavioral changes significantly influence transmission dynamics. behavior epidemiology-informed neural networks outperform the standard physics-informed neural networks in prediction accuracy, in robustness to noise, in computational efficiency. And these findings emphasize the necessity of behavior-aware epidemic models. So this is what the findings of the study by Torku and others basically illustrated. Thank you.
All right, thank you very much. So any questions so far? Any questions before I ask mine?
Yes,
yes, Doc. Yes, Doc.
Okay.
Okay.
So Ima, go first.
Okay. Senior Ransford, we checked the compliance model and we saw that the compliance algorithm was applied to only the deterministic work. Is it a case where we would have to apply only to that, or it can also be added to the stochastic model? Because the compliance algorithm was only applied to the deterministic model.
Yes, thank you very much. Thank you, So with the compliance factor, we applied it in the absence of the stochastic variable or stochastic entity to look at its behavior. But there are instances you can incorporate the two to look at, because compliance is just one aspect of the dynamics, the behavior of the population. You understand? But when we talk about stochasticity, it's actually a lot of inconsistency across data, across behavior infatuations, like people randomly behaving anyhow, like anything that can randomize the dynamics. So we can incorporate the two together and work with it, but this work actually did not consider that.
Okay. Another one, the training sets and the testing sets, which were used for training 80% and the testing set for 20. And we also
Could you come loudly so that I hear you clearly, please?
Please, can you hear me?
Yeah, I can hear you now.
When we were checking for the training and testing of the model, as usual, you used 80% for the training and then 20% for testing.
Yeah.
In the case where the compliance model has been incorporated, is there a way we can also train the model, since it's a neural network kind of algorithm that we are using? Can we train the compliance model to also check how effective it is using the testing and the training sets?
Okay, you are asking, let me get this clear. You are asking whether the model can still be trained on the data after incorporating the compliance factor in the model. Is that what you're asking?
Yes. Can we also train to know whether the algorithms used earlier would also work on the compliance model? Because incorporating the compliance model produced a different kind of model because new factors have been introduced. So I wanted to know if it can also be tested, trained and tested to check its actual performance.
It can, because the compliance factor in the model there is going to affect the behavior of the parameters. Do you understand?
Okay.
So it can be used because the parameters will not remain the same when you incorporate the compliance factor there. Do you get what I'm saying?
Yes.
Yeah, so it can be used to train that as well, to look at how best the model can predict when the compliance factor is incorporated into it.
Okay, thank you.
Okay, Samuel.
Yeah, Senior Ransford. On the training of the data, I was able to get this. You said the beta, you've trained
Training of the model.
Yeah, in the fitting aspect.
The fitting, okay.
Yeah. You said the transmission rate, that is beta, is being trained, and that of the recovery. don't you consider this? The recovery is known, and what I can say, it is the unknown one that we use in the fitting, but the recovery can be known, but the transmission is unknown. So don't you think that of the transmission should be the one should be trained in the fitting?
Okay, thank you. You see, when it comes to choosing which parameters to train and predict, and then which of them to keep fixed, it gets to do with the dynamics of the disease in question here. If you look at the behavior of the COVID-19 virus, with the recovery rate basically depends on the infected class. You know that, right? Are you with
Yeah,
me?
yeah,
Yeah, it depends on
yeah,
the
I'm with you.
infected. Good. So if that we are to predict the transmission rates, remember the transmission rate has direct bearing with the recovery rate because it is the people who get infected that will recover and move to the R class. So this
Okay,
ideally should be the best parameters to train and predict in this situation.
okay, okay. So you consider the recovery rates as the one that you have been trained for the data fitting
The
based
the
on the
transmission the transmission rate, recovery rate, but all the other parameters were kept fixed.
affix. Yeah, for that one,
Yes.
I do understand that one. Okay, thank you.
Welcome. Hello.
I think dog will take over. Dog will take from here.
Yes,
Yeah,
please.
all right, good. So I think you did good, give a good presentation and stuff. So for instance, let's go to, but some things that you didn't present clearly, were